Welcome back, everyone. In this video, I'll begin going over the lecture for the areas and distance section. The point of this section, what we will see is that we won't really see doing the antiderivative. What we're going to do is we're going to have this section and talk about how areas somewhat are related to the antiderivative, specifically using the examples of distance and velocity. And what we're going to do is really just talk about how to figure out how to calculate or estimate the distance traveled based on the velocity, or how to figure out by approximation and also using limits to figure out areas under curves. Now that's going to be a very specific wording when we say area under curves, but without further ado, we'll go ahead and jump into it. Most of the section is centered around the areas part, and then we just specifically talk about the distances part when the curve y equals f of x is actually a velocity. All right, so kind of a preview here. We'll see in a couple sections that the idea of antiderivatives is related to the topic of finding areas, and this will be very important. This is probably the most important result of calculus. And we'll see it's so important that it's got a special name in the future. All right, but right now, what we're going to think about is calculus is going to allow us to find areas of more general shapes. So over here on the left, I just have a whole bunch of shapes that you know how to find the area for without calculus. This is a triangle, we have a circle, a rectangle, trapezoid, and a pentagon. Now you might not know the bottom two area formulas off the top of your head, and if you don't, that's perfectly reasonable because I don't either, but they exist. And the point is you don't need calculus at all to do them. You only need that area formula, pretty much the length, the width, the radius, whatever shape you're talking about. Well, with calculus, what it's going to allow us to do is it's going to allow us to say, hey, we have a function graph, and for some reason, I want to find the area between the function graph and the x-axis. So that's why this area here is stopping at the x-axis and going up to the function. It sort of makes this random shape, and I want to cut off at some x values a and b. So I want to find the area of this shape. Well, calculus, as long as we can work with this curve's formula, like let's say this is sort of like a sine function, but it could also be, really a lot of different things. There's many things we'll be able to find the area with. We're going to be able to find the area of this. And without calculus, this is impossible. Maybe not impossible, but in general, extremely hard, and you would never want to try to find the area of this. So pretty much think of any shape that you have an area formula for, that you've probably been exposed to those, all of them already. None of them are being hidden from you. Well, now we're going to be able to go through and actually do really infinitely more shapes, find the areas with calculus. Right. And one thing I already kind of mentioned here and I said in Word, but I want to go ahead and rewrite. Oftentimes we use the words area under the curve. And when we say area under the curve, there's kind of a few assumptions we're assuming here. And if these assumptions are broken in future sections, then what we'll do is we'll adapt and learn how to actually find the area. But for this section, area under the curve, what we mean is that we want the area between y equals f of x and the x-axis. So we specifically want the area between those on the closed interval a to b. Now that's always going to be true. We're going to have to be on a closed interval. In general, you can do areas that actually go from a infinity to infinity, but they have to be very special functions, and that is not a topic for us right now. And then the other thing is that by assuming this picture, we're kind of assuming that f of x is above the x-axis. And that's something that's not always going to be true. So when that doesn't happen, we're going to have to adapt to that. But in this section, we'll just assume f of x is greater than or equal to 0. That means it's above, or at least on the x-axis. So it can touch the x-axis, it can be above it, but main thing is we don't want it below the x-axis, at least for this section. All right, so the idea is to actually figure out the area is to start with approximating areas using rectangles. And in general, there are three kinds of quote unquote rectangles that you can do to approximate. So what I have here already pre-drawn a little bit is, you see I have the words left, midpoint, and right written. Now, when you go ahead and approximate the area under the curve, you will be given directions as far as which one to do. The point I'm going to try to make here is that it doesn't matter which one you're told. Your formula ultimately is going to be the same, just depending on which one of these is going to affect the x values you end up plugging in. All right, but we can use left endpoint, right endpoint, and midpoint. And that might not make any sense yet, but what we have to do, and for this example, I have y equals x squared drawn from x equals 0 to 1. So let's say we wanted to find the area under the curve from 0 to 1 of y equals x squared. So we have this sort of bent shape. I don't want to shade it in because I'm not actually trying to do the area yet, but I have this shape that I want to find the area inside. Definitely not something that we have a formula for because it's a kind of a curvy shape. It's related to a parabola. It's not a circle. It's not a triangle or anything like that. Well, just for the ease of drawing the picture, I'm using 3 rectangles. I'm going to use 3 rectangles, and generally you can have any number of rectangles, and the more you use, the better your approximation is going to be. But the way it works is like this, and I'll spend most of the time talking about the left one, and then we'll just apply it to the midpoint and right as well. So what I've gone ahead and done is I have 0 and 1, and I drew these 2 green lines in between because I wanted to make 3 bases for my rectangles. There's 1, there's 2, and there's 3. All right, so, and that's going to be the true for all of these. So I drew these same exact ones, and they're equal length. So you can actually figure out what their length is. It would be 1/3 because we're breaking up the interval that has length 1 from 0 to 1 into 3 equal lengths. But just for the sake of this problem, I'm not trying to actually calculate anything, so I'm not going to clutter it anymore. All right, so if we wanted to approximate with the left rectangles, the idea is the following. For each of your intervals, so this is interval 1 here, it's going from starting from 0 until our first point. We want to take the leftmost x value, oops, that is not how you spell value, but we want to take the left x value on our interval on the x-axis. And then what we want to do is do that for each one of these. So for the second one here, I have the left x values right here. And then for the third one, I have the left x values right here. And you can see I have 3 x values picked out. I have the left one for each interval. It will have some overlap with the right when we graph that, but just focus on the left here. So the first interval here, I take the left point, which is at x equals 0. Then the middle interval, I take the left point, which is right here. And then the rightmost interval, the third rectangle I'm going to make, the left interval is over here. And what you do is you take your point, you draw a line straight up until you hit the curve itself, and then you form a rectangle based on that. Now it's pretty hard to explain just for the first one at x equals 0 because the y value is also 0. So I'm actually going to start with this one. And typically we work left from right, but just for the sake of explaining this for the first time, we're going to work right to left. So what I do is I take my point here, I draw straight up. Now the important thing is to remember that this is the left point. So this is being used for the third rectangle base right here. So what I want to do is go ahead and, since this is the left side of the rectangle I'm going to form, I'm going to draw it to the right until I get to my x value endpoint. Now this is supposed to go straight across to make a rectangle and then go straight down. All right, and this is rectangle 3. It's the first one we drew because it's just probably the easiest one to draw, but the idea is that we would find the area of this thing. Then for rectangle 2, we do the same pattern. We draw a line straight up until we hit the curve, and then we go to the right because this is the leftmost part of what the middle or the second rectangle is going to be. We go until its x value endpoint, which will hit exactly where the other one starts. And it goes down. So that is rectangle 2. And then the leftmost rectangle, because the height is actually 0, you just draw a straight line. There is no area being drawn. Okay. And the point here is if we wanted to actually put some numbers to these things, because we could, we're not going to yet, but we could. What we could is go ahead and plug in the appropriate x values here, figure out their heights, and then the base lengths, and we know how to find the area of a rectangle. So we would add up the area of these 3 rectangles. And that would be our left approximation. I'm going to jump to the right one because the midpoint, it's not really more challenging necessarily, but it probably makes more sense after we do the right one, since the right one's so similar to the left. Well, all you do is you do the same thing, except you use the right endpoints. So our first interval is from 0 to the first green. Now the rightmost point here is actually on the green part, and that will be the y value we use, or the x value we use for the first one. If you want, you can just kind of draw in as you go, because now you've seen how it works. So this goes straight up. Because we're now talking about the right, this is the height of the rectangle for the right or leftmost triangle. I want to keep wanting to say triangle, but leftmost rectangle here. So we go to the left until it's starting x value, which is at 0. And then we draw straight down, and that's rectangle 1. Then for the middle interval, the next interval, the rightmost x value is over here. Draw a line straight up. It's not very straight, but let me redraw it. It's supposed to be straight. We draw a line straight up until we hit the curve. Then we go to the left until we get to this x value. And if it helps to mark this one off, you can sort of just draw this line up here, and that's supposed to be flat. So that's another rectangle. And then the final one for rectangle 3, the rightmost x value is at x equals 1. And we draw this all the way up, straight up. And then we go to the left until we get to the starting x value for this final rectangle, which would be where this one ended right here. And then we can draw this straight up to sort of attach it. But these would be the right x values and the right endpoint rectangles. But the same idea is going to apply. You know, pretty much the only thing that's going to change with all of these is just the x value we're plugging in. So for the left one, we plugged in this x value, this x value, and this x value. For the right one, we plugged in this x value, this x value, and this x value, which dictates the height of the rectangle. But the width or the base is always the same. It's just 1/3 because we broke it up the same exact way. Now the midpoint, it just sounds exactly like it does. Instead of doing the right, sorry, that would be the left. Instead of doing the left or the right, you pick the middle. We don't deal with the midpoint much, but I just want to go ahead and show you that this is another way to do it. That you could really pick any point you want inside here. You don't even have to pick the midpoint every time. One could be the left, one could be the right. But the idea is, if you're approximating these things, you want to just pick one, left or right, maybe the midpoint, and just do, you know, the straightforward thing and do just the right or just the left. Okay, but the midpoint, the idea is exactly the same. You draw straight up until you hit the curve. Now, because you're in the middle of this interval, you go to the left until you get to the start. You go to the right until you get to the end. And that is our first rectangle. And then you pick the middle of the next interval, somewhere around there. And you do the same thing. I like to sort of dash the midpoint just because I want to point out to myself it's the middle and I have to go both ways. So I have to go to the right until I get to the stopping point there. And then I also have to go to the left until I get to the stopping point there. And then the last one, the middle is about right here. And I'll do the same thing. I go to the right until I hit the end, which is at x equals 1. And then go straight down. And then I go to the right until I get to the starting x value right here. And if you want, you can draw up and attach like that. And so this would be the middle approximation. if you added up all the areas of these rectangles. But the emphasis, again, just to repeat it, is that the only thing that's going to change when we write down a formula for using areas of rectangles to approximate it is the x value you plug in. All right, so the idea with approximating is, quote unquote, relatively simple, because what we're doing is we're really just visualizing what x values to plug in, the base of the rectangle, so how wide it is. This one is 1/3, no matter which one we're choosing. And then we multiply base times height, pretty much. Base is sort of like the width or something. So width times height, length times height, whichever two ways that makes the most sense. I think base and height makes the most sense, but the area of this rectangle is just base times height. And then what you do is you just add up the three areas. So what I've already gone ahead and done here is I've redrawn the right endpoint one just to talk about, more specifically what we would do. Well, how do you figure out the area of the x1? Or sorry, the area of 1 here, the first rectangle. So this one over here. Well, the area is base times height. And yes, for rectangles, you are used to length times width, so you can use length times width. Just realize that base times height probably makes more sense for our picture. The base, b, well, the base b, we can figure out numbers because we specified 0 and 1. It's divided by 3, but in general, the base, actually, let me go ahead and write base instead of letter b, because this could be a little confusing since we used the letter b in our formula. In general, instead of using 0 and 1, we're going to have b and a. And the base is going to be b minus a over n. Now, if you want to see why that's true, when for our example, we have b, the ending x value is 1, a, the starting x value is 0, and n, which is going to be the number of rectangles, so we haven't specified that yet. But you have to be told that in a problem, that is 3. So for our example, we have b minus a over n equals 1 minus 0 over 3, which is 1/3. And that's exactly if, for our example, if we wanted to go ahead and plug in the base, we have 1/3, because each of these would be of length 1/3. We have 3 of them to add up to 1. But in general, base is b minus a over n. And then the height here, what's the height of rectangle 1? Well, think about just looking at the picture. Which x value did we pick to draw up to hit the curve? Well, this was the right one, so we picked this right here, which is x1. I'm calling x1. So the height here is f of x1 because it's the y value when we plugged in x1. Now, what is the area of rectangle 2? Well, the base times the height. The base is always the same, so that's really a big point here is, b minus a over n. So when I go ahead and do area of rectangle 3, base times height, we're going to get b minus a over n again. What is the height of rectangle 2 here? Well, you should say it's f of x2, because the height of rectangle 2 here is where the curve is hitting the x value right here, which is x2. And, in general, we would call that f of x2. And then finally, x3, the height is this point right here. Yeah, we could pretty easily figure that out because that's actually 1 for our problem, and we have y equals x squared, so it should just be 1 squared. But to keep it in general terms, this would be f of x3. And now the point is, if you add all these together, I'm sort of getting at the point where the formula that I'm going to write below is going to come from. But if you add all these together, so if I go ahead and add all these together, the point is you have b minus a over n times f of x1 plus b minus a over n times f of x2 plus b minus a over n times f of x3. And while we don't really know what anything is here in general, we have a b minus a over n in common. We can factor it out. And then we have f of x1 plus f of x2 plus f of x3. And now once again, for our problem, we had n equals 3 specifically, so I could plug in 3 here. But if you had n equals 4, then we would have plus f of x4. If we had 5 rectangles, we would have plus f of x5, and so on. Now, when we follow that pattern, there is a relatively straightforward formula. So if you want to approximate the area under the curve of y equals f of x on the closed interval a to b using n equal length intervals, then there is a straightforward formula. But once again, we are making an assumption here that f of x is greater than or equal to 0. Because if it's not, then what's happening? Well, it's going to go below, and we haven't really talked about below. What's going to happen when the curve is below? We're not sure yet. So just keep in mind that this formula is going to assume f of x is greater than 0. But the area approximate equals, it's b minus a over n, and then in brackets, you just add up the x values. So f of x1, you add up the f of x values. So f of x1 plus f of x2 plus f of x3. And the point is we don't really know what n is, so it's up to f of x sub n. We have n x values that we're going to plug in. And the reason why this formula, I don't like to give a more specific formula, is you should figure out the x values you're going to plug in based on the problem. There are formulas out there if you want to go and find them, very specific. They say, oh, well, if you're doing the right endpoint, then it's this. If you're doing the left endpoint, it's this. If you're doing the midpoint, it's this. That's great. But what's going to happen here is you're going to have to figure out the x values for the right endpoint. You're going to have to figure out the x values for the left endpoint or the midpoint. Whichever one you do, you're going to have to figure out all those x values. So if you're already going to figure them out, why memorize different formulas when it's all really just the same formula? All right, so you do have to know this formula, but in words, kind of as we were describing here, what this is saying is figure out the nx values to plug in. So like for this one, x1, x2, x3, we could have figured out the actual x values to plug in. Then plug in f of x and add together. So that's what this is saying. We plug in all of our x values separately, of course, and then maybe this is 1, this is 2, this is 8. You add them all together, then multiply by the b minus a over n. All right, so figure all that out, multiply by the b minus a over n, which is the base or the width of the rectangle, and you'll be good to go. Now, if you're not comfortable with what we call summation notation, sigma notation, you should watch the preliminary video that I went over, but this is also written this way. So area approximation using rectangles is b minus a over n. And then you have the sum or sigma notation, I equals 1 to n of f of x subscript I. All right, all this means, just hopefully you watch this video, the preliminary video if you're stuck here, but all this means is we plug in I equals, that should be a 1. All this means we plug in I equals 1. We start with plugging I equals 1. We add, we plug in I equals 2. We add, we plug in I equals 3. We add until we get to whatever n is. So this means exactly the same as this, but this formula is going to become more important when we go through the section. So probably refer to it like this when it's easier than writing out. Let's say if we had n equals 10, we wouldn't want to really write this out. So just keep that in mind. All right, but in the next video, we'll actually start working the problems. We really got the base for everything in this section down now, except for the last little bit. So I will see you in the next video.